Okay, so the second part of today, this is our topic, signals, video recording will be here, but let's start from this one. So digital signals, what we are talking about when we are talking about digital signals, for this course especially. So, okay, this is kind of silly, but anyways, a digital signal processing example, voice recording. You have a recorder and basically how the voice recording process goes. What's that? Amplifier. Amplifier amplifies the small signal you get from the microphone. Actually, usually you have the bias in amplifier, so you also provide the power for the microphone, for the GPs. Okay, what else? We have low pass filter, right? Then there's sample and hold circuit, which is usually part of A to D converter. Next part would be the A to D conversion. And all of this actually, what kind of signals you have there? So first you have a very small signal on your oscilloscope screen, say few millivolts, maybe max 100 millivolts. But then the A to D converter has usually few volt region that it does the conversion. So what you want to do is to fill that few volts as well as possible. So try to keep those in bound, of course, plus and minus bound, but you need to then do some amplification for the signal. And after that, it's within the bounds of the A to D conversion. Then it has this high frequency noise there. That's why you need to have analog low pass filter. So even it's a digital system, you need some analog filtering because of aliasing effect. Have you heard of that one? Probably. Yeah, you have been awake on the electronics classes. So preventing the aliasing, you need a low pass filter, and then you'd have the sample hold. Okay, which holds the signal value at the constant level until it's converted. Okay, depending on the A to D conversion type, it might not be needed. For example, sigma delta does integration of the signal, which basically does the same thing. But if you have successive approximation type of A to D converter, then you must have this kind of sample hold circuit. Okay, so now we have discrete time signal. And at the end, the A to D conversion actually just you quantize the levels. There's no half bits or quarter bits on the A to D conversion. Believe me. Some people actually try to kind of increase the resolution by starting the averaging. Yes, you have averaging. You may have these decimal bits, but they don't mean anything. If they did, this chip manufacturer would have sold the device with higher bits for better profit. Okay, but anyways, so quantization, meaning the nearest value will be then selected, something like that. Usually it's actually either higher value or lower value because of the electronics. Okay, so on the beginning, we have analog signal, meaning the continuous time, continuous the value. So it can have any value on the space. Sampled signal. Okay, it's just that we have this sample hold circuit that stops the signal value. Now we have discrete time signal, but still any value. And last one, digital signal. We have both discrete time and discrete value. So only at certain times and with some bits resolution. And now this is the one we can actually put on the microcontroller, since its microcontroller have very limited amount of memory. So memory-wise, if you have 8-bit A to D conversion, which is not much, then you need that 1 byte there. If it's longer, then you need some 2 bytes, 3 bytes, 4 bytes for each sample. Then you collect the time series of those. You will start actually making tables for those. Okay. Whoa. And we have a cat. So let's see. Yes, this course mostly works with the sampled signals, not too much about the quantized, I mean time-wise. We have only the last part, the embedded, for the embedded systems. The last part is about what happens when you start having the quantization of this data, and especially quantization of the filter characteristics. This actually is the sampled signal analog is pretty much simpler, but also if you have a floating point arithmetics, what you can always add by adding money to the design, then basically it's exactly the same as this sampled signal mathematics. I'm not adding the quantization of the value too early, only at the end, and just to see what is the effect compared to the this continuous value signals. Okay, and here the sampled signal means basically that, okay, the form is something like x of n, which is a tabulated value, equals to x signal x at sampling point n. Another assumption we do, which helps, well, it makes this post-digital signal processing possible. We always have a constant sampling rate. Otherwise, it's just a random signal on random space. You cannot do much with that one. It's like watching a thermometer only once in a week in arbitrary times. It doesn't say what kind of week it was. So sampling rate, some marking sampling rate is usually capital F with the sign S there. Then sampling interval, meaning the sample time between two samples, it's marked with T of S, time of the sampling, sample time. That's 1 over Fs, simple. And then there's the sampling theorem or Shannon theorem. In order to reproduce the signal, you must have at least 2 samples for each period. It's quite straightforward to think about if you have a trash bin. Ouch! So close, still so far away. Okay, if you have a sign like that, and think of how many samples you must have to show this one. Well, I would say 1 here, another here would give me a good. And then basically here, if you have, say, less samples than that, then you do not see the big picture anymore. For example, here 1, but then another one would be, well, in worst case here. So then it looks like that kind of signal compared to with this, if you have at least twice, then this already starts to look like a periodic signal. And there's a picture of a typical aliasing case. The real signal is the blue one, and then red ones are the sampled with the too low sampling frequency. Okay, what does it mean for the electronics? First of all, you need to have high enough sampling rate for the signal. So you need to know something about the signal frequencies, how fast they are, how often, if it is periodic. City on that one, you need to know about it. So you would need to know the power spectrum of the signal. What else? Then you have noise on the system. Always when you measure anything, you have noise. So if there are any high frequency noise there, you need to use the low pass filter to basically filter them out before sampling. Okay, that's why I have the anti-aliasing filter on the schematic of the design. Okay, yeah. Then we have this digital signal and a couple of things which are basically for the digitized signal. Okay, this is when we have quantized values, and there is a signal to quantization noise ratio formula. Simple. Okay, but that also it's a nice formula to find out. Okay, if you have some music, you want to have something like at least 80 decibels of the dynamic range for that recording, and that actually gives you that you need to have at least, say, 12 bits would be almost enough. It's 70 some dB. Not quite yet, but still, say, nearby. 12 bits is okay for audio like, speech or something like that. Okay. And where does this, say, so-called CD quality, how many of you actually have any CDs anymore? Oh, you have CDs, yeah, some history. Okay, CD was just great when it came, so it made the whole big difference compared to the, okay, now we probably have more people with a plastic, these LPs. How many of you have LPs? I do. Yeah, we have more. Yeah, they're coming in. Real sound with all the noise. But anyways, the CD quality signal was, or is actually some sort of industry standard. Where does that 44.1 kilohertz sampling rate, for example, for this computer come from? Well, it comes from the human ear physiology. So you can hear up to about 20 kilohertz signals. I cannot anymore. So basically, then you must have at least 40 kilohertz sampling rate. And for some reason, some people found out, okay, let's put it 44.1 kilohertz. Yeah, that comes actually from the fact that you need to also have some room for the anti-aliasing filter. Okay, so you need to have about that 10% of the this band need to be reserved for the slope of the anti-aliasing filter. Okay, that's what gives the sampling rate. Yeah, it means 44.1 thousand samples per second. Yeah. Then again, the dynamic range for music, the sound pressure levels are typically 20 to 100 dBA. When you compress that one to the digital form, you want to have the, or actually, with the pulse code modulation, PCM, which is just the values of the digitized signal, you do not have any compression other than the well, what the bits give you. So this actually, in order to have better than 80 decibels of signal to quantization noise ratio, you need at least that, was it 13 bits resolution. Okay, but that's a little bit awkward for any computer system since byte is 8 bits. FPGA, no problem. You can have 13-bit system to save some serious amount of the design space on the FPGAs. But for the any processor-based, you would be wasting a lot of bits. So it's better to actually feel that. Use 2 bytes instead of 1.5 bytes or 1 and 5/8 bytes. Okay, so that's where the CD quality actually comes, the 16-bit resolution. So 16 bits, 44.1 kilosamples per second. That's PCM, that's CD quality PCM signal. Okay. Fundamentals, more fundamentals. In order to actually analyze and handle the systems, we need a couple of basic signal sequences. Just like in, well, for example, in analog systems, you need these Laplace transforms. Yeah, you need those in order to analyze how the analog system actually works. The same way here, or actually for the analog systems, you have this step function what you put into the system to see what is the step response of the analog system. Then you can compare it with, measuring it with oscilloscope, or measure it and then you can go back and try to figure out what is the transfer function of the system. On digital domain, the principles are the same, but here we can use the Dirac's delta function or discrete Dirac's delta function. Unit impulse, meaning it's just a test vector you put into the system, which is all the other values are 0 except on the time event 0. So time index 0. Analogy for that one on the analog world would be very short, infinite value signal. Not practical with the electronics. Usually you get above 1000 volts, then the electronic is no more. Yeah. ESD discharge would be close to that one. It's not a good test vector, except for the ESD sensitivity. Another test vector helps you to compare the digital system with corresponding analog system, which is simply the Heaviside, sampled Heaviside function. So this is what you remember from the electronic systems with all these transfer functions on S-plane and stuff like that. Yeah, you're still getting the some fever from that. Yeah, heavy stuff, Heaviside stuff, and a couple of formulas how the this discrete delta and this unit step function, Heaviside function actually correlate. Okay, yeah. So you can make one from another by just simple mathematics. The nice kind of mathematically interesting part is the lowest formula there. Basically, it states that any random signal can be described by the delta function, actually delayed delta function multiplied by the signal. Okay, so basically what it means, This formula gives you possibility to sample of those the signals, and then the total signal is actually superposition of the sampled ones. Yeah. Kind of, sort of. Okay, so those are the two commonly used the kind of test vectors, unit impulse and unit step. Unit impulse will have use on defining or determining what kind of system we have in impulse response way. It also helps you to do the filtering, and it also helps you to analyze the spectrum of the system and that kind of things. Unit step, basically, it's nice analogy to the how to test these analog systems. What else we have? Then we have plenty of different kind of periodic systems or periodic signals. A kind of slight warning about periodicity. On analog domain, meaning the analog systems or analog signals, we can always find if a signal is periodic, there's always a base period, and then basically you can find the shortest base period, capital T, on that formula, that it basically the signal repeats itself every t time. Okay. Yes. Oh, all. It means all. Sorry, I used to do too much mathematics on university, so it means for all. Okay, that's actually it's like xt equals to xt plus the capital T for all. Wait a minute. The last letter is here should be real. Okay. Yeah, there's small mistake on this formula actually. But anyways, that a upside down a means all, for all t belongs to real numbers. That capital T is not correct. I will change that at some point. When you sample that periodic signal, it does not necessarily need to be periodic anymore. Have you covered already on mathematics a Gibbs phenomenon? Probably not. Okay, yeah. So this is actually one way of explaining Gibbs phenomenon. When you take a spectrum analyzer, have you used spectrum analyzer on laboratory? Okay. If you have an old-fashioned long, the analog spectrum analyzer, good heavens, they are gone. For a poor frequency, you would just see one peak. But you have digital sampling oscilloscope, and you have a single frequency, the sinusoids, for example. You will get envelope like this. Or actually, they probably usually go like that. That's artifact due to this effect. Since in digital domain, this is not exactly periodic. You cannot find a integer index that you will continue the same, exactly the same values on the next period. So as you can see on here, okay, if you start sampling like that, the next, the upper half is sampled on different points, that one too, that one too. Only on the case that you have exactly matched the those sample points, for example, like that. But that has to be exactly. Then you will see single peak on the spectrum, which practically never happens. You don't have such a luck unless you are measuring the internal oscillator of the oscilloscope which you are doing this data analysis anyways. That's the only way you can get exact frequencies out of the otherwise they will be more or less envelopes on the spectrum analyzer. Okay, so periodicity is not that straightforward on sampled signals. And that's why we actually need to do the spectrum analysis and understand what the spectrum actually, what you see there. It might have some artifacts because of the sampling. Well, it has some artifacts because of the sampling. Okay. Frequency space. So this far we had more or less sampling on the time space, but then of course we just do some mathematical tricks to show the same signal on frequency space or system. One way, if you have a periodic signal, then you can present this as a sum of the frequency components, harmonic frequency series. So this is the Fourier series. Remember that one from the mathematics. Good. Yeah, we are not doing those Fourier series. That's the last time you usually see those. Haha. Just to remind you, okay, whatever signal is, there's always, you can do the spectrum analysis of it. That's all you need to know. And it does not really matter for the signal perspective. Do you handle it on time space or frequency space? Same thing for the systems. Just like on the analog systems, you did those horrific transfer functions in S-plane. But then the spectrum analysis was really easy. You just replace the S with J omega. Done. Okay. Or do the this Laplace tricks to get the step response of the system. Okay. So don't be worried about frequency space. It's just the different representation of the same system or signal. Okay, most of the signals in the world are random or should be considered as random. Some things about those. So basically what is random signal is simply a signal which has unpredictable values. You cannot do the forecast for the next value, just like the weather. That's very random. Oh, do you want to have a weather forecast which is as equally as accurate as the Finnish Meteorological Service or any other does? Look at window today. It will be like that tomorrow at the same time. The same accuracy as these 24-hour forecasts. Okay. Yeah. But anyways, that's just some trivia. The nature is a bitch. it's unpredictable. But anyway, so it means that when we are dealing with that kind of signals, then we can measure only statistical and spectral properties, and that's it. Just like say some examples of what noise sources. Wind noise is a good one. When you are outside, we have wind noise on the microphone, for example, small scale. You can actually do some cancellation techniques that work as long as you have some sort of regularity on your noise. But when the wind changes rapidly, then the noise cancellation does not work anymore for a while. Yeah, it's adaptive filter, meaning it tunes the filter based on the what it analyzes. Okay, another one, shot noise in electronics. That's one way of doing a simple white noise generator. Just put some small current through resistor and measure the voltage. It's white noise. Johnson's noise in electronics. That's thermal effect. The shot noise is, well, you know that electrons are single charge carriers, and when you have slow enough current, then they start just dropping through the resistor, not really flowing. Shot noise, that's thermal movement of charge carriers, and that's also something that you just need to deal with. Two typical kind of random noise the distributions. One is natural or Gaussian, so-called. So with big numbers, any noise is Gaussian, says a mathematician. Close enough. Or if you have smaller numbers and it's kind of like throwing a dice event, then it's Poisson distribution. Statistics classes, those were probably the two distributions. Fortunately, nature does not actually use much more of. It's either of those plus than the spectral properties. Okay, and some of the statistics, how to basically do the some sort of quick analysis, what kind of distribution the signal has. You just start recording the values and then calculate how many of those values in a region fit into each of those value boxes. That's how you get there. Normally distributed random numbers, for example, on the right, and on the left there is the Poisson distributed with 1000 samples. Okay, some statistical analysis. Okay, then a few tools. Correlation. Correlation is simple mathematical operation when you can what you can use to find similarities on signal. For example, on radar technology, you send a short pulse, radar pulse to the atmosphere. Yeah. And then it returns back, and then you have some really fast processing units that compare by correlation the pulse that was sent and what was returned. It is very effective of removing all the noise components other than which are exactly the same as the returning signal or the sending signal. So it basically just it's like sending the hand that way and then it returns back, and you have this same match there, and you start calculating how well they correlate, and bang, that's where they correlate exactly, and you get a sharp return. So radar technology is based on correlation. Either analog systems or the currently I think all the radar are more or less digital the systems on the starting from front end. Okay, so correlation actually measures the similarity. Autocorrelation measures the self-similarity of the signal. And this is just to take the signal and correlate it with itself. Maybe I should draw something here. So are you familiar already with the correlation? Did the math or physics teacher tell you? No? Okay. Correlation between two signals. For example, like this and maybe like that. What you do is, well, X and Y. You calculate the sum or integral of one compared to time shifted another one. I need to check which way is this one. M plus N. Okay, so when you do that, so basically you just do time shifting of the other signal here. And if these signals are totally random, well, that's not a good example. Those are way too complex signals. If you have one bump here and another similar enough bump here, and you start calculating this sum so that you modify this delay on another signal, you basically get more or less zero until you have delay M, where you have shifted the other signal exactly on the same position with the other one. Boop. And there we have a high correlation on time shift M. Okay. Now think of this as the radar signal. Okay, let's have a radar signal. So we have the outgoing pulse here, and then we have the echo. And we do autocorrelation. So when we have shifted, let's put this one, Z. Okay. When we have shifted this signal so that this the signal we sent is the same as the signal which is returning. So this one, we would have the maximum correlation here at time Z. So basically, this is showing directly the distance how far this echo came from. Okay, that's how any radar actually will function. If you want to know more about radars, go to Otaniemi. They have really nice radar technology classes there. But after all this signal analysis for the radar kind of systems, it's basically just correlation analysis. You just sample fast enough and then collect the data, do actually autocorrelation, which has both the sent signal and return signal the same. The only small problem is to have enough of dynamic range to fit those on the same system. Yes, you have a question. Yes. It does actually because of, well, if you have totally random signals, they do not correlate at all. If they have similarity, then it gives you a big number. Yes, we are multiplying these values at each time difference and then calculate the sum of it. So it's basically taking that part and that part, point by point multiplication and calculate the sum. Simple, but I think I might actually have a exercise on that one. If not today, then on next week exercise. I'll make sure that we have an exercise on that one. Otherwise, it's kind of, yeah, I know it's hard to kind of imagine what happens there. So, but anyways, each of these points here represent one time delay. So every time, for example, the first part here is zero lag means you are multiplying those together like that, or signal by signal like this, calculate the sum. Next one would be with the time difference of 1. You just shift this one and do the calculations again, and so on and so on and so on. So this takes quite a lot of time actually to do all the calculations. So with the 1000 points for each point here, you do 1000 multiplications. And if you want, say, 1000 the time delays here, then you need to calculate 1 million of multiplications. But calculations are cheap. Just add the power to the processing, and that's it. Just add money. Yeah. And autocorrelation, as I said, it's just measuring the one signal and calculate the similarity of signal to itself. Okay. And then you can do also in this frequency domain with Fourier transforms, but yeah, that's nice in mathematics, but you need to see that one. Correlation examples. Okay, this is something that could be demonstrated, except that I don't have any loudspeaker here. Well, maybe on that one, but then I would need a separate microphone. So that's something if you have an external loudspeaker and a microphone, you can do this kind of demonstration yourself. Just put a loudspeaker like this, then point this microphone the same direction, then you put, for example, paper to have something reflection back to there, and you just start recording, for example, chirp pulses. Put the chirp pulses on this loudspeaker and just play around and do the demonstration for the next time. Okay. All right. What happens then if we actually do the same as previous, but do some time shift in separate way? So, okay. So if we do n minus m, oh, actually n minus m, not plus, but n, meaning that we are time shifting the other axis here. Wait a minute, is that correct? M n minus m. Yeah, m n minus m. So we are time reversing the other signal. Doesn't make any sense, does it? It actually does, since this is the convolution, which is equal to frequency space multiplication. So what is your filter doing? What filter does the signal? Analog filter. Yeah, measure this low pass filter, the amplitude responses, right? And then tested everything and something like that. But anyways, the convolution is same as roughly multiplying the signal with the amplitude response. So basically, it's filtering operation. So you can filter the signal either by multiplying the signal with the corresponding frequency response on frequency space, or calculate the convolution on time space, which is easier for calculations. in computer? The convolution, of course. Then you don't need to do any time-consuming operations between time and frequency space on limited amount of computing power. Okay, linear filtering based on convolution, yeah. So that one, mathematically, it's the linear convolution is the same as a frequency space multiplication. So if you do the Fourier transform of the system impulse response and Fourier transform with the system input and take the inverse Fourier transform. That one, it's the same as this linear convolution. Yeah, you have done the on signals course. You did this Laplace transform on analog systems and try to figure out what is the step response. Okay, exactly the same thing here. Okay, signal to noise ratio, just to remind you, you are electronic students, I don't need to remind you of that. You know decibels, right? That's the one you eat with your breakfast, you know. Spectrum analysis. Nothing magic about that one, it's just the Fourier transformation. We have an exercise on the Fourier transformation also, so nothing to see here. And that was this Gibbs phenomenon I was talking about when you sample, when you have the spectrum of a sampled sinusoid, for example, it's never a peak. It has this envelope because of the sampling. Good. All right. Now I see some faces. What's that? That is spectrogram. Is there anyone who is actually being on watching birds? I mean real birds. Not birdies, but birds. Okay. One way of recognizing this singing song of a bird is to record it and show a spectrogram of it. So it's basically time frequency map of where the frequencies are. On this one I have the spectrogram of a chirp signal, meaning the varying frequency, linearly varying from 0 to look like 500 hertz here. Frequencies changing by time. So when you have a interesting signal which has some frequency variations, then the spectrogram is the correct tool to find out when there was a something interesting on the signal, in which frequency range. Okay. Wow. That was the theory part. There are some self-study questions on that link. It's anonymous questionnaire just to, practice or test if you were awake. Couple of simple questions. Go ahead, have fun, check it out. Otherwise, you can always comment. I like feedback. So if you have something to comment, for example, on these slides, so just use the comment tool on your Google. You can actually, I allowed some commenting of this document, so please feel free to send comments. Otherwise, any questions? Okay, let's have 15 minutes break to get some coffee. And after the break, please be here exactly at 3:30 p.m. because we are starting to have fun with the MATLAB. Okay, 15 minutes break.